Welcome to Visual Double Star Astrometry. This lecture is an introduction to visual double star research. It provides the big picture of visual double star research, although with emphasis on one particular type of visual double stars, visual binaries. We will learn about Johannes Kepler's 3 laws of planetary motion that helped launch the age of modern science. William Herschel observed visual double stars, hoping that their parallactic motion would reveal their distances. Instead, he discovered binary stars, pairs of gravitationally bound stars. Analysis of binary star orbits showed that these stars also followed Kepler's 3 laws of planetary motion. The universe ran with mathematical precision. Observations of binary stars over decades or centuries can lead to the establishment of their orbits. Reduction and analysis of these orbits can lead in turn to determining the most important stellar parameter of all, the masses of stars. Astrometry is the branch of astronomy concerned with the measurement of the positions and apparent motions of celestial objects in the sky and the factors that can affect them. Astrometry is the oldest astronomical observational technique and was in full bloom well before Galileo first used his telescope for astronomical observations in 1608. In fact, the Babylonians and the Egyptians, to a lesser extent, made astrometric observations of the sun, moon, and planets at the dawn of civilization, attempting to understand their rather complex motions against the fixed backgrounds of stars over time. It is not surprising that most early theoretical models of the universe placed the Earth at the center. There was not any good evidence at that time to place the sun at the center, although it was suggested and appropriately rejected for lack of evidence. An early Greek model placed the moon, sun, and each planet, each on their own invisible crystalline sphere. The stars were mere points of light on an outermost sphere. Because the planets sometimes reverse their motions with respect to the background stars, their occasional retrograde motion, each planet was also placed on its own little rotating sphere, as shown in the illustration. The main orbit of a planet around the Earth was the deferent, while the small orbit the planet made to produce a retrograde loop was called the epicycle. Claudius Ptolemy, a Greek mathematician, astronomer, and the director of the Great Library at Alexandria, developed a very sophisticated mathematical model of the Earth-centered universe that mathematically predicted the future locations of the planets against the background stars, including their retrograde motion. It was 1,500 years before Nicholas Copernicus suggested a sun-centered model of the universe with equivalent mathematical predictive power. The pre-telescopic highlight of astrometry was Tycho Brahe's highly precise positional measurements, particularly of the planet Mars with respect to background stars. Tycho's measurements were an order of magnitude more precise than those that preceded his. They clearly showed that the current models of the universe were woefully inadequate. It might be noted that our planetary system was the universe in those days. Tycho didn't have the mathematical wherewithal to develop a model of planetary motion that could match the precision of his data, so he hired a mathematician, Johannes Kepler, to analyze his voluminous data, by hand, of course. After years of analyzing Tycho's data of the position of Mars against the background stars, Kepler discovered that 2 key assumptions that had previously been made about planetary orbits were wrong. First, planets did not orbit the sun in perfect circles. Rather, they orbited the sun in ellipses. The fit of the Mars positional data to a circle was very poor indeed, while the fit to an ellipse was quite good. Kepler's first law is that the orbit of a planet around the sun is an ellipse. However, something still seemed to be slightly wrong with Kepler's model of planetary motion, the heart of what was then the model of the cosmos. Always the perfectionist and a bit of a maverick, Kepler searched for refinements to his model of the universe that would provide an even better fit to the observational data. After a number of false starts, he questioned the ancient assumption that planets orbit the sun at a constant velocity. Perhaps they moved a bit faster when they were closer to the sun in their elliptical orbit, and a bit slower when they were farther away. After trying various possibilities, he found one that fit the data almost perfectly. He found that planets orbiting the sun swept out equal areas in equal times. Truly brilliant. This is Kepler's second law. Shown is the equal area swept out in equal times rule. A month of motion when the planet is near the sun sweeps out the same area as a month when the planet is far from the sun. To complete his model of the cosmos, Kepler noticed empirically that there was a relationship between the time it took the planets to orbit the sun, their period in Earth years, and their relative distances from the sun. Specifically, the semi-major axes of their elliptical orbits in astronomical units. An astronomical unit is the average distance from the Earth to the sun. At the time, we did not know the actual distance from the Earth to the sun, but Kepler knew the relative distances of the planets from the sun in Earth-Sun astronomical units, AUs. Kepler found that the square of the orbital periods of each planet in Earth years, p squared, was proportional to the cube of semi-major axis of each planet in astronomical units, AUs, a cubed. The proportionality constant was the dynamical mass, m sub d. The proportional relationship is Kepler's third law. The dynamical mass, m sub d, is the sum of the masses of the primary and secondary stars, m sub p and m sub s. Kepler's third law was dead on when a log-log plot is made for all of the planets of their semi-major axes in astronomical units cubed versus their periods in Earth years squared. The beautiful relationship shown in the figure appears. This relationship was a major empirical scientific discovery by Kepler. The dawn of modern science. Copernicus's initial mathematical model of a sun-centered universe, Tycho's observations, Kepler's analysis and three laws, and Galileo's telescopic observations launched what many historians consider to be the modern era of science. For the first time, humanity had a precise mathematical model of the cosmos that matched the best observations to a remarkable degree. It was totally amazing that the universe could be described so precisely with mathematics. Galileo thought that the sun was the center of the universe and stars were just points of light on a nearby sphere. For those, contrary to Galileo, who thought stars were distant suns, he suggested they should look for and observe stars that appeared close together, double stars. Specifically, Galileo suggested observations of doubles that had one bright star and one faint star. He assumed that they just happened by pure chance to appear close together along the line of sight from Earth. If the bright star was nearby and the faint one far away, then the nearby star should shift its position with respect to the faint star over a 6-month period due to the orbit of the Earth around the sun. This shifting is called parallax. When Earth is at position 1 in June, the near star appears at B with respect to the background stars. 6 months later, when Earth is at position 2, the near star appears to have shifted to A with respect to the distant background stars. The angle theta is called the parallax, while the distance d is the distance from our sun in parsecs, a contraction of parallax arcseconds. 1 parsec is about 3.26 light years, the distance light travels in a year. Following up on Galileo's suggestion, William Herschel began measurements of the separation and position angles of double stars in earnest in 1779. The position angle of a double star is the angle that a line from the bright primary star to the fainter secondary star makes with respect to celestial north. The position angle is measured from north, traditionally down for astronomers, through east on the right, south up, and west to the left. The position angle is measured in degrees from north. The separation of a double star is the angular distance between the primary and secondary stars and is measured in arcseconds, or for close doubles, in a fraction of an arcsecond. An arcsecond is a very small angle. A circle is divided into 360 degrees, while a degree is divided into 60 arc minutes, and an arc minute is divided into 60 arc seconds. Thus, there are 1,296,000 arc seconds in a circle. An arc second is the angle that a dime extends at a distance of about a mile. There are several types of visual double stars. Optical doubles are the chance line-of-sight alignment of two stars in the sky. The two stars are separated from each other by huge distances, and despite their appearance, the two stars are unrelated to each other. Herschel thought that all stars had about the same intrinsic luminosity. They would be about the same brightness if they were at the same distance. Thus, he was expecting to see optical doubles with the nearby star appearing to be brighter and the more distant star appearing to be fainter. It might be noted that we now know that optical doubles, not surprisingly, are the most common type of double stars by a wide margin. Shortly after he began observing double stars, Herschel reported his observations of 269 double stars to the Royal Society. Continued observations led a couple of decades later to Herschel's somewhat unexpected conclusion in 1803 that a number of the double stars he had been observing were not optical doubles as expected, but rather were pairs of gravitationally bound stars, a type of double star he called binaries. Herschel could tell that the stars were gravitationally bound because the secondary star, with respect to the primary star, was moving in an arc. Herschel's discovery of binaries suggested that Newton's law of universal gravitation could be acting on distant stars. An observation of a double star yields a measured position angle theta and a separation rho. The observation is made at some specific date and time t. These three values, theta, rho, and t, are the big three of double star astrometry. Since visual binaries typically take decades, centuries, or even millennia to trace out their orbits, it is usually sufficient to provide time, t, as a year and the fractional part of a year to 5 decimal places. These three parameters, theta, rho, and t, define an astrometric observation of a binary star. It is these observations, patiently gathered by many astronomers over the years and decades, that are brought together to form a series of points that approximate an ellipse. Given a set of observations of some binary gathered over the years, with your own observation perhaps being the most recent, these points should form roughly an ellipse. If everyone's observational accuracy was perfect, all the points would fall right on an ellipse, as called for by Kepler's first law. However, all observations have some error, so there will be some scatter to the points. We can, however, mathematically solve for some best fit apparent elliptical orbit. In doing this, we are applying Kepler's first law. The apparent orbit is what we see along the line of sight from Earth. Of course, apparent orbits are not true orbits, except by coincidence. Viewed along the line of sight from Earth, an orbit will appear skinnier than it really would be if we viewed the binaries from straight above or below. Thus, we need to rotate the apparent orbit in two orthogonal angles to give us the true orbit. How are we going to determine these two angles? If you guessed apply Kepler's second law, please immediately go to the head of the class. There will be one orientation of the orbit in three-dimensional space that will best fit the dates on which the observations were made. Now that we have solved for and determined what the true orbit is, an ellipse, Kepler's first law, properly oriented in space such that equal areas are swept out in equal times, Kepler's second law, how can we determine the masses of the stars, our true goal? As you will recall, Kepler's third law states that the period in years squared is proportional to the semi-major axis of the true ellipse in astronomical units, AUs, cubed, where P is the period in years, A is the semi-major axis in astronomical units, and MD is the dynamical mass of the two stars in units of solar mass. The dynamical mass is the sum of the two stellar masses, M1 plus M2. It should be noted that the units of the semi-major axis are astronomical units, not arcseconds. Thus, we need to know the actual physical separation, not just the apparent angular separation. Determining the actual physical separation, given the observed angular separation, requires that we know the distance from Earth to the binary pair. Simple trigonometry then yields the physical separation. Distances to binary and other stars are determined through the measurement of parallaxes, the displacement of nearby stars against distant stars as the Earth orbits the Sun. Parallaxes of over 100,000 stars were measured with the Hipparcos Orbiting Astrometric Telescope placed in orbit by the European Space Agency in 1989, with observations made over the next several years. Hipparcos parallaxes are used to translate semi-major angles to physical distances. Gaia, launched by ESA in December of 2013, is now providing much more accurate parallaxes on many more binaries. At last, we have the dynamical masses of binaries, a significant and difficult accomplishment that takes international teamwork for decades and sometimes centuries. A final step is to accurately split the dynamical mass, which is the sum of the masses of the two stars, into individual stellar masses. This can be done by combining the astrometric orbital information with spectral information on the radial velocities of the two stars, a procedure beyond the scope of this seminar. Stars condense from clouds of gas and dust. Somewhat randomly, some stars are truly massive, while others are mere featherweights. Almost all of the major characteristics of stars are determined primarily by their initial mass. A star's size, brightness, temperature, and lifetime are all very sensitively related to stellar mass. Thus, to understand stars and their life cycles, we need to know their masses to high accuracy. The most famous of all astronomical diagrams is the Hertzsprung-Russell, or HR diagram, as it is usually called. Although we will not dwell on the HR diagram, a glance at it will show that the stellar mass is the key parameter. The patient observations made by astronomers over the many years needed to establish binary orbits helps to establish stellar masses. An observation by a student team can, if published, make a contribution to this international, multi-generational endeavor that now extends for over 2 centuries.